All right, welcome to another lovely week here in Math 202. Before we get back into the whole double integrals and playing around with changing bounds and all that, I wanted to open it up for any homework questions because there are some homeworks that are due tonight. Do want to remind you that one of them that said it was due tonight, which I believe was 5.2, I extended to next Monday. So we will just notice that that is the case. I think there are only 2 sets that are due tonight. But I already see in the chat box, we've got questions 29 and 30. Can you guys tell me which section that's from?
Mine is from section 5.1, double integrals of rectangular regions.
Okay. All right, so we've got 28 through 30 on 5.1, and then Ralph threw in that he'd like to see number 8 from 3.4. All right, so let us then go and take a look at these. So I'll go ahead and share my screen and we'll go see what these guys look like. Okay, so Jacob, you just said all the ones in 5.1 deal with finding bounds for a double integral. So we may not have to do all of them, but we'll do at least a representative of them until we're starting to feel a little bit better about bounds. Does that sound good? Okay, so let's go take a look at that one for Ralph first from section, what was it, 3.4. Good old motion in space. The silence is deafening. All right. Let's go take a look at number 8 here. All right, so we've got a function, e to the minus t cosine t, e to the t sine t. And we want to find the unit tangent vector, the unit normal vector, the normal acceleration, and tangential acceleration at t equals pi over 2. All right, so Seamus says the answer to this is a monster. Sometimes they are, for sure. Sometimes these things can get really, really gnarly. Thanks for the warning. The one thing, though, that we do have going for us is that we're at a specific t. And so since we're at a specific t, that can help us a little bit when it comes time to find like big T and big N, because we don't necessarily need to carry out the entire function. And I'll show you what I mean here. So let me go to a whiteboard and we'll work this guy out. All right. Okay, so my suggestion with these is to go ahead and just start with your R and find R prime and R double prime. We're going to need to know R prime for sure, because R prime is going to allow us to figure out big T. And the reason that I suggest we go and we find R double prime is that that's going to help us actually find AN and AT. We have some formulas for finding the normal and tangential portions of the acceleration, right? And so we might as well make use of those, and they involve V and A. So remember, V is R prime. So we can go ahead and get that guy real quick. That's going to be a minus e to the minus t cosine t minus e to the minus t sine t. So I just did the product rule. on this guy, right? And then the other portion is going to be e to the t sine t plus e to the t cosine t. So that's our r prime. So then our double prime, which is going to be our a, just differentiate one more time. So this one's going to be a little bit longer, but let's just see what we get here. So we get e to the minus t cosine t plus e to the minus t sine t plus e to the minus t sine t minus e to the minus t cosine t. So that's a product rule on those two pieces. And then similarly over here, we're going to get e to the t sine t plus e to the t cosine t plus e to the t cosine t minus e to the t sine t. All right, so how are we doing so far? Not too bad, I hope. All right, now, because we know we're at a specific point, I'm going to go ahead and plug those in. All right, so for example, so we're at t equals pi over 2, right? So our r is going to be e to the minus pi over 2 cosine of pi over 2 e to the pi over 2 sine of pi over 2. But I know cosine and sine of pi over 2, so I can actually plug those in. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. So like there's our position vector. Similarly, I can get our v. If I plug that in again, remember all the cosines go to 0 and the sines just go to 1. So we get minus e to the minus pi over 2 comma e to the pi over 2. So there's our v at this point, and then I can do the same thing for a. Again, cosines go to 0, so I'm left with a 2 e to the minus pi over 2, because I get 1 from each of those. And then in terms of the y, again, the cosines go to 0, the sines, they cancel each other out. So there's my acceleration vector. So this is one nice thing about being at a specific place. Then I can go ahead and calculate my vectors for these positions. And the reason that I really did that is now I don't actually have to do any more calculus. I can dive right into finding my t. So big T, I know points in the direction of my velocity. So if this is my velocity vector, I just have to divide by its magnitude. Right? So t is r prime divided by the magnitude of r prime. Okay, well that's that minus e to the minus pi over 2 comma e to the pi over 2 divided by its magnitude. Well, its magnitude is going to be the square root of e to the minus pi plus e to the pi. So that was this thing squared and that thing squared. So there's the answer to part 1, I think, because we want the t, right? Okay, now I'm not going to get n just yet. I'm going to skip that for a second. But let's get the a sub n and a sub t. All right, now it kind of depends whether we're talking the vector or we're talking the magnitude, right, with that a sub n or a sub t, because like a sub t as a vector is going to be v dotted with a over the magnitude of v times big T. Well, we got big T, so we can just deal with that. But this now we can go ahead and find using the vectors that we just calculated. So like if we do v dotted with a, you're going to get minus 2 e to the minus pi. So that's those two multiplied together. These two give us a 0. Divided by the magnitude of v. Okay, well, that's all of this stuff. Times t. And we actually just found t. Yeah, that's a vector. So we can multiply that by this. And what we end up with as the vector, the tangential acceleration piece, is 2e to the minus 3 pi over 2, comma, minus 2e to the minus pi over 2, divided by e to the minus pi plus e to the pi. And yes, I know we could simplify that some way, but I'm just going to leave it like that. All right, so there's our AT. Now, if we were just looking for the magnitude of this, because I know that when I wrote this and showed you guys, I looked at AT as just the magnitude of it. So if all we wanted was the magnitude, that would be this portion. Since t is a normal vector, or unit vector, I mean, it's length 1. This is the magnitude. So this is the magnitude of the tangential acceleration, but this itself is the tangential acceleration. Okay, so before I move on, how are we doing so far?
Good.
We're following, we're all right?
All I know is I actually picked the do a similar question option. It gave me t equals 0.
Oh, you lucky bugger.
Yeah.
Man, if I could have t equals 0, I'd be happy. All right, well, anyway, so here's AT. So now what I'm going to find is AN. Because I'm going to use the fact that AN plus AT is equal to A. So the vector AN is equal to A minus AT. Well, I've got an A. I've got an AT. So we can just subtract those. So I'm not actually going to carry this out any further, but hopefully you see how easy it is just to take this minus the other one. I'm just too lazy to write it all out. All right, and so then once we're there, if I want to find n, I'm just going to take that AN that we just found and divide it by its magnitude. And that'll get me my n. We have another option back here when we did t. Remember, we can find AN by swapping these two and changing the sign on one of them. We just need to know which one to change the sign on, and that one we'd probably want to draw a graph of this, get a feel for what direction it's moving at pi over 2, and then we'd know which way to point it. But that's an alternative way to find a big N as opposed to this. So, but that really only worked because it was 2D. If this was 3D, what I was describing down here with finding a sub n and then dividing by its magnitude, that will always work in 3D as well. So it's probably better to know this general process instead of just the shortcut, which only works if you're in 2D. So Seamus was right. The answer to this is kind of a monster. I mean, I've seen worse, but yeah, it's monster enough that I don't want to actually finish the problem. But anyway, I believe that was Ralph's question, right? So are you feeling better about this, Ralph? Kind of? I'll definitely take kind of. Is there anything I can do to make it less kind of and more yes? Yeah, Matthew, you're right that certain versions of this problem are going to be terrible depending upon what we're plugging in, right? Like plugging in 0 would have been beautiful, right? But all right. Okay, well then let's step off of this one since we kind of have a feel for where we're going. And it's the same process no matter what your R is. You can start here and work your way down. So at least we got that going for us. So let's go look at those other ones. Let me stop sharing this and then we'll go back to the homework page. But this time we'll go find homework set 5.1 because we got a string that we want to see from there. I guess when it comes to a problem like the one we just did and how sometimes with a t, a t value, it can get a little bit ugly and gnarly. I guess it's always good to have this sort of in your mind in the math world is that mathematicians especially, we don't really care how ugly it gets. We care more, can you do it? Is it possible to get it done? And we just tolerate the temporary, ugliness. And so to me, and it's a little bit weird for me because I definitely straddle the world of the math and sciences, because the math side of me is like, sweet, there is a way to do it. We know how to do it. We can get an answer. Everything is good. But then, of course, the scientist in me is like, ugh, these numbers are horrible. But also realize that in the science world, you're going to be doing it for a reason. It's not just, in a vacuum. And so if we think about it that way, we know that at some point a decimal approximation is going to be fine. And so you think back to that one that we were just doing where we had the e to the minus pi over 2 over the square root of e to the pi plus e to the minus pi or whatever. You would just calculate that to a handful of decimals and you'd be good. And that would definitely speed up the process. So anyway, bought enough time to bring up this homework set. All right, so let's go look. I have on my notes 28 through 30. So let's go take a look at those guys.
Yeah, Bruce, if you just cover 28, you can skip 29.
Okay.
Because they're asking the same question.
All right. So 28, it says we want to find an upper and lower bound for this integral. So R, the region that we're looking at, is given by these bounds. So it's a rectangle. Our x's are between 0 and 5, and our y's are between 0 and 3. And then they tell us one more thing. They tell us that the function itself is always greater than or equal to 0 and always less than or equal to 210. And they say, let's find an upper and a lower bound for this integral. All right, well, before we actually do that, let's think about what that double integral is doing. That's telling us the volume under this surface, but above the given region, right? So in here, again, our x is 0 to 5, our y's are 0 to 3. So we've got this surface. There is a volume under it. And that's what this is getting us. So basically, we're just trying to say what's an upper bound and a lower bound for that area. All right, so let me go ahead and go back to a whiteboard here real quick. Let me clear this guy off. All right. So again, we're doing the double integral over the region. I'm just going to write f of xy because I don't really care what it is right now. But we were told that the region was x's are between 0 and 5, and y's are between 0 and 3. So let's practice plotting that real quick. So that's our region. So just like with single variable functions, we integrate over an interval on the real number line. Double integrals, we evaluate over a region in the plane. And this one just happens to be rectangular. So if we wanted to, so we could even do this to get a specific number, we could set this up as, say, a dy dx. So this would be integration man is standing vertically. So he's going to look like this. And notice that everywhere, integration man, his head is on y equals 3. And his feet are on y equals 0. And then in terms of how far he's going to march along on the x's, he's going to start at 0 and go to 5. So like this would be the bounds on this thing if we actually wanted to calculate the specific value. All right, but it turns out that's not necessary. I really did this just to help you guys practice and see what it looks like, how integration man can help us form it. But what we're going to do to estimate or at least get bounds on this is use the fact that we were told that this function, it's always bigger than or equal to 0. And it's always less than or equal to 210 in this region. All right, so let's just think about biggest possible value we could get for this volume, right? Because we want to have a similar, let's have bounds on this integral. So worst case, when I say worst, just biggest case, is where the function's equal to 210, and the function was equal to 210 everywhere in this region. So think about what that surface would look like. What would that surface look like if your function, this two variable function, was equal to 210?
Would it just be a level plane?
Yeah, that's exactly it. It'd be a level plane that's resting up over here. So think about what that volume would be. What kind of shape would that volume be then?
Just a box, a rectangular box.
It would just be a box. So think about what that volume of the box would be, right? Volume equals length times width times height. Okay, so length and width would be these two dimensions, so 3 and 5. And then again, worst case would be that everywhere it's 210. And so we could multiply those together, which I think is 3150. So for sure, I know the volume is less than 3,150. It could be less, right? It definitely could be less. In fact, it probably will be, especially from the fact that we saw that shape. It wasn't just that plane. But at least that's a maximum I know for sure. Okay, so this would be our maximum volume. So what about minimum volume? Well, again,
0
times width times height. So it's going to be 3 times 5 times 0. Because the smallest could be if it was 0 everywhere. Okay, well, so then it's 0. So I actually have a pretty big range of what this integral could give us. It's going to be something between 0 and 3150. But those I know for sure. 100%. I know that this double integral is going to be somewhere between that. So in essence, all I did, like look at how I set this thing up. I've got the two tens, and the 0, right? Those things, those came from the bounds on my function. And then where did the 3 and the 5 come from?
Bounds.
Yeah, those were the bounds. In fact, that's the area of the region, right? That's the area of R. So in essence, this 3150, this was the area times that max. And the 0 was the area times the min. So if we'd been told that the minimum for this function in that entire region was, say, 10, then I would have taken 10 times that 15 and known that the actual value of this integral is somewhere between 3150 and 150. Or if I was told the maximum value was 90, then I would have taken 90 times that area, and that would have gotten me a different max.
So Bruce, question 29 does not give the lower or upper bound of the function value. So how
Okay.
do you find those 0 and 210?
Well, let's go take a look at that. But before we do that, any questions on or how we did this so far?
No.
No, we're all right?
Yeah.
Okay, so let's go take a look at number 29. So I'll stop sharing that screen and go share the other one. Okay, so here's the other one. So again, it says find an upper and lower bound for the function x squared y squared over this region, where region again is a rectangle. And so really the question is, what's the lowest value that this function is going to take on in this region? And what's the greatest value? And then we can use those to approximate, or not approximate, but give bounds for the integral. Now, I don't want to necessarily trust their picture for a couple of reasons. I never trust people's pictures just because people make mistakes. But also, it's kind of hard to see, like, if this is that highest point, what is its value? I mean, is it 80? Or is it near 80? You know what I mean? Like, could it be 79? Could it be 82, right? And what's this low value? Oh, good Lord, there's no way I can tell from this graph. So, but let's just kind of look at this function and see if we can make sense of it. So I'm going to go to the whiteboard here. And let's start with the function again. So the function was f of xy equals x squared y squared. All right, and then the bounds, -1 to 3 and -1 to 1. Okay, so x's were between -1 and 3, and the y's were between -1 and 1. All right, so let's draw that region real quick. So there's x equals -1, x equals 3, y is -1, y is +1. So there's our region. Okay, so for this one, we're going to have to be smart about it. We're going to have to look at this function. We're going to have to look at this and think about what happens as our x's and y's jump around in here. So first of all, let's talk minimum. Since these are both being squared, I'm not going to get any kind of a negative number out. So the smallest possible value we get with this function anyway would be 0. But that's only because these are x squared and y squared. If one of those had been, say, a cube, then I could have taken on negative numbers and all that. But I already know, just in general, that x squared, y squared is going to be greater than or equal to 0. So is it going to equal 0 somewhere in this region?
Yeah.
Yeah, the answer to that is yes. In fact, lots of places. Anywhere x is 0 or anywhere y is 0. So any of the points on the axes are going to be one of the spots where we actually get 0. So even in my region, I know that this is a minimum value, right? It's going to happen anywhere on there or on there. So you take any of those points and you got it. Cool, this is starting to look like the Norwegian flag. All right, so now the question is there a maximum number that it will take on? Well, what's going to make this the biggest?
When x is 3 and y is 1.
Yeah, so when we get our biggest possible x and our biggest possible y, and so that's actually going to occur in a couple of places. But right here and right there are both going to give me my biggest possible function value, right? Since I'm squaring x and y, the bigger x is, the bigger my number comes out. The bigger y is, the bigger my number comes out. And so the largest x, or the furthest from 0, x is 3. So 3 squared. And then the biggest y we're going to get is plus or minus 1. And it doesn't matter which, because when we square it, we get the same number, which is 9. So they didn't tell me the bounds on this, but I was able to figure it out by looking at that function. And now if I want to think about what the double integral bounds are going to be, I just need to multiply by the area. Okay, well the area of this thing is length 4, right, from -1 to 3, and its height or width 2. So it'll be 0 times 8. This one's going to be 9 times 8. So I know for sure that double integral is going to be somewhere between 0 and 72.
Gotcha. Thank you, Bruce.
Yeah, you're welcome. And so like before, we could have actually done the integral. And if you do the integral, this one would be the double integral of x squared, y squared. Let's set it up as a, say, dx dy this time. So now integration man is sideways. So here are a couple of representative integration men. His head is always over here on x equals 3. His feet are always on x equals -1. And then the y's, he walks from -1 to +1. So this would get us the actual value. And if you calculate that, you'll see you're between 0 and 72. And I'm going to guess much closer to 0 than 72. I think it's going to be on the lower side. But that's just guess. Mostly because we're not straying much outside of plus or -1. Anyway, so better for that one. All right, so let's go take a look at the last guy here that was requested, number 30. So same set, but next question. All right, so this one, we've got our function, x, y, sine of x squared y. So we want to be under this, right? We're bounded above by this and below by the xy plane. And we're going to look on the rectangular region, x from 0 to 1, y from 0 to pi. Okay, so kind of your standard sort of deal here. So let's set up the double integral and see how we're going to go about it. All right, so to the whiteboard. All right, so, oops. Let's erase that real quick and go back to black. All right, so we're going to do a double integral. Our function is going to be xy sine of x squared y. All right, so I'm just going to generically call it, we're going to go over the region. We're going to have a dA. So hopefully you kind of caught that. If we don't want to specify which way we're setting it up, we're just going to write a dA. So that can be a dx dy or dy dx. And then we'll just say over the region. This way we don't have to worry about the bounds until we decide how we want to set it up. But again, the region looks like this. We're going from 0 to 1, and we're going from 0 to pi in the y. So there's our r. But we like rectangular regions, right? Rectangular regions make it so that the bounds are always the same. So we are constant, I should say. So we actually have two choices here. We can do it as a dy dx. So we'll set it up as a dy dx. Or we can do it as a dx dy. So let's set them both up and then we'll decide which one we want to do. So if it's dy dx, integration man is vertical. So his feet are on 0, his head is on pi. So 0 to pi. And then the x's are going to range from 0 to 1. So that's what that one would look like. For the other one, the x's, dx, now integration man is sideways, his head is on 1. His feet are on 0, so 0, 1. And then the y's range from 0 to pi. And so this is always the case. I don't know if you've noticed this when you have a rectangular region. If you do it in the opposite order, the only thing that changes are the bounds swap. They flip-flop. All right, so we good with the setups of these two?
Yeah.
All right, so now we have to decide which one we want to do. Do we want to integrate with respect to x, or do we want to integrate with respect to y? Okay, so Victor just said, if we use dx dy, it looks like we can use u sub. So that's the second one. So if we let u equal x squared y, then du is 2xy. Right? Remember, y is constant, so it'll be 2xy. So we're only off by 2. Yep, you're definitely right. If we choose the second one, we can do a u sub. What about the first one? If we integrate with respect to y, notice that the u sub won't work. If we do u equals x squared y, then du is x squared. And we don't have that out here. So what would you have to use for this first one if you didn't use u sub?
By parts.
Yeah, y by parts, Bradley.
Because of multiplication.
Yeah, we've got y times sine of x squared y. And so if u sub doesn't work, that means you're going to have to do integration by parts. I would rather not do integration by parts. So let's do u sub. So we'll do this second one, and we're going to do a u equals x squared y. So then du is equal to a 2xy dx. So that turns this integral into a 1/2 sine of u du. So that's just the inner one. I'll just put little stars here for our bounds. We'll replace those in a minute. But this is the substitution to make it an integral in terms of u. So that's going to give us a minus 1/2 cosine of u, which if we turn that back into the x's and y's, we're going to have minus 1/2 cosine of x squared y evaluated at 0 and 1. And those are getting put in for our x's, right? Those were x values. So what we're going to end up with then is an integral from 0 to pi of minus 1/2 cosine of y, right? 1 squared y, minus a negative 1/2, so plus 1/2 cosine of 0, which is 1. Okay, so we just evaluated the inner integral we got here. And now we're left with still integrating with respect to y. And before we do that though, any questions on what I did over here? So everyone should thank Victor for spotting that, because that is definitely the easier way to integrate. And that's something that I do all the time. When I'm presented with something like this and I have multiple options, I try to think through what are the steps going to be to do these integrals, which one will be easier, which one will be faster, and that's how I choose. It won't matter. I mean, if you had done the other one, you're going to get to the exact same value. You just may have done a little bit more work. Okay, so where does the x squared go when we replaced u equal x squared y? It didn't go anywhere. I put it back in. So right down here, you see the x squared y. That's still in there for the u. Are you talking about when I went to the next step? Okay, so in this, going from the bottom right to over here to the left, I plugged in 1 and 0 in for my x, because now I'm evaluating that integral. And those guys are going in for x because this was a dx. Okay, yeah, so that is the one thing we definitely have to watch out for, is make sure you're plugging into the proper letter. And it's really easy to forget about that. And I agree, Victor, I tend to do dy dx if possible. So that's kind of my go-to, but just in case you switch it around, just be careful, watch it. All right, so now we're ready to finish this out. We're going to get a minus 1/2 sine of y plus 1/2 y that we're now going to evaluate at 0 and pi. Well, sine of pi is 0. So we get 0 plus 1/2 pi. So cool, 1/2 pi. And then when we plug in 0, sine of 0 is also 0, and 1/2 y is 0. So it turns out that that volume under that surface over this region is just good old pi over 2, 1/2 pi, something around 1.57. All right. So, okay for that one?
What was the question again? Just evaluate and find the
Yep, it was
volume?
just evaluate this integral,
Okay.
which in essence was finding the volume under that surface over that region. But as we'll see later, it's, well, we just calculated whatever the double integral, what we're trying to add up for that double integral. But yeah, this number is just pi over 2. But I think this actually does illustrate something, and I'm just going to mention that I was working with somebody earlier, and we kind of ran into an issue of, oh yeah, integration by parts. double integrals are going to require you to remember all your different integration techniques. And there are a lot of them, and we tend not to like them, right? Integration by parts, trig substitution, partial fractions, like all that stuff. But it's going to come back. And since we now have options, right? I mean, we've got this big or here. You can do it either way. Since we have options, the stronger you are with your different integration techniques, the more you see them and when you can apply them, the easier it's going to be to pick the path of least resistance. And you want to do that. And that's not just coming from a lazy guy who doesn't like to do work and assumes that you guys are the same way. That's just from like reality. We want to do it the fastest, easiest way. You know, when you go out and you get your job doing whatever for whomever, they're going to want you to do things in a, you know, quick and accurate way. And if you can find something that saves you a little time, they're going to love you for it, right? So we want to think that way here too. Think integration techniques and go, oh, geez, what do we have to use? And this one just screamed at me, oh yeah, U-sub. Let's do that because U-sub is fast. All right, enough preaching on this one. We feeling good? Feeling better about the homeworks?
Oh yeah.
I hope. All right, well, I think today we're going to go ahead and just practice some more of this swapping bounds, and you know, we won't necessarily go through the integrals because I know that for the most part we have technology that can help us with it, but it's never a bad idea to remember how to do them, right? So like with that one we just did, I used zero technology and still got a nice answer of pi over 2, right? Just remember those things. Okay, well, let me go ahead then and jump over to the whiteboard, and I will see you guys in just 1 second. All right. So really the trick with any of these double integrals is getting your bounds. Getting your bounds set right, recognizing how we can do it one way or the other, how one way may be easier than another, and the like. So what I want to do, again, is not necessarily do any specific integrals. We'll just go generic functions, but let's practice setting these things up. Setting them up both as a dy dx and as a dx dy, and just sort of get used to the process. All right, so I think we're probably good though on rectangular regions, right? Rectangular regions are pretty easy. You just swap the bounds as you swap the integrals, and everything is good. So let's look at those that are a little bit more complicated. And again, we'll just kind of start easy. So let's say this is my region. So we're going to integrate some function, f of xy. I'll put it dA with our r, but let me draw the region for you. Okay, so this region is going to be this triangle. And this triangle, I'm going to give you the coordinates of the vertices. So this is the origin, so 0, 0, obviously. Let's say that this is 5, 0, and this one is 5, 2. Okay, so this is R. And what I'd like to do is actually write it out both as a dy dx and as a dx dy. All right, so let's go ahead and just get these two set up. So the first one, let's make this the dy dx. And the second one, we'll make dx dy. And let's use integration man to help us out. So we'll start with the first one, dy dx. So which way does integration man go? Is he up and down, or is he left and right? Is he standing up, or is he lying down?
Standing up.
Okay, good. He's standing up. So integration man is going to do this. So there's a little integration man. He's getting taller. There's a little micro integration man, and so on. So he's going to look like this. All right, so let's think about head and feet. We'll start with his feet. His feet are always on the y-axis, or sorry, the x-axis. So that's going to be y equals 0. So we'll put 0 right there for his lower bound. Okay, so then what about his head? Well, his head is always on this line. So let's see if we get an equation of that line.
Yeah. Y.
So Victor just said, Victor just shut out, put in the chat, x equals y. What do you guys think? Yeah, I don't think x equal y is going to quite work. Since the x and y coordinates are the same. So Seamus, you have y equals 2/5 x. How'd you get that? Okay, so you just did the slope of the line, rise over run. So we are going up 2 and over 5. So we know that its slope is 2/5. So if we go to the good old y equals mx plus b, we're going to have y equals 2/5 x. And then the b is our y-intercept, which is 0. So the equation of this line is y equals 2/5 x. So that's going to be the upper bound. So the head is y equals 2/5 x. So we're going to write here 2/5 x. Okay, so we got integration man in terms of his feet and his head. So then, of course, we're left with, now that we've got that, how far is he marching? And in the x's, he's going from 0 out to 5. So as dy dx, there are our bounds. Okay, so now let's turn him sideways. So let's set up the other one and see what this is going to look like. So I'm going to go ahead and erase the red integration men. And we'll make them green this time. And so now, here are some representative integration men. All right, so now if we look at integration man, his head is always on the same line. And his feet are also always on the same line. It's just they're different lines than before. Right? So his head is always on x equals 5. So the upper bound on this one is going to be 5. But the lower bound is going to be his, where this slanted line is. So what are we going to put as the lower bound?
X equals 5/2 y.
Good, we're going to put 5/2 y. Because these are x equals. So you actually have to solve this thing for x. And if you solve it for x, it's x equals 5/2 y. So that's why that's going in as our lower bound. So real quick, Victor earlier mentioned that he usually does dy dx, right? Or at least up to this point in playing with the homeworks and everything. And I think that is the general where people want to go, because we're used to writing these things as y equals, right? Think about all the functions and anything you've ever done we always solve for y. So we're kind of in that habit. And so I think it is really natural to do a dy dx, like have that be the place where we're going, right? So when you do dx dy, realize we're solving for x. So it's just a slightly different idea. All right, so now, of course, all that's left is to do the y's, and integration man this time is going to start at 0 and work his way up to 2. So the y bounds on this are going to be 0 and 2. All right, so both of those are good. Both are equally valid. Both of them are fine. And in terms of this one, which one I would do, it's really going to depend on what f looks like. Because f may be one of those things that's really easy to integrate with respect to y and not x, or vice versa. And so I'm just going to play that by ear. But this region doesn't really suggest doing it one way or the other, right? The region itself, nah, it's totally fine. Just like the rectangular region, the problem you guys just asked me about, the one that had the xy sine of x squared y or whatever. That one, the region, it was a rectangle. I don't care. Bounds are the bounds. It's not a big deal. It was the function itself that determined how I wanted to do it. And so when it comes to double integrals, it's kind of a balance. Sometimes it's the region that will really force you to do it a certain way. Other times it's the function that's really going to push you to do it a certain way. And if you're lucky, they both are trying to push you in the same direction, right? They're both trying to tell you, hey, do it with x first. Or they're both trying to tell you do it with y first. When you get into those weird situations where the region is suggesting one way and the function's suggesting the other way, the function wins. The function always wins. So if you've got a function that can be integrated one way but not the other, you do it, right? Go back to my statement about mathematicians. We do things because we can, regardless if they're hard, right? Well, if there's a way that can be done and the other one can't, you go that way. All right, well, anyway, so there's a triangular region. Let's try this one. So again, we're just going to do a generic f of x, y. I shouldn't erase this dA, but this time, here's our region. This region is going to be a semicircular region. Okay, so it's a semicircle, or at least pretend that it's a semicircle. And it's radius 2. And the region's going to be the piece that's in here. Okay, so there's our R. But we're going to do the same thing. We're going to set this up so that we're integrating once as a dy dx, the other as a dx dy. All right, well, I can pretty much recycle all of this. I think I might need a little more space though, so let's do this. All right, so let's start off with dy dx. It's probably the way that you want to do this anyway. So let's get him set up. Dy dx. He's going to be vertical this time, integration man. So there's an integration man example. There's another one. There's a really tall one. Okay, so there's integration man. So what is determining his head?
That quarter of the circle from the x-axis up.
Okay, so this circle, this piece up here, right? What's determining his feet?
The negative of that.
Okay, so it's also the circle, right? So this is one where both his head and his feet are at the circle. So Victor, he said, can you split it so that the feet is on y equals 0? Yes, you could. You could do two different integrals. You could do one for the top half and one for the bottom half. but I don't want to do two integrals. I just want to do it as one. But yes, you definitely can split it like that.
Flip
The
them.
one thing that I'm going to warn you, just all I'm saying, the one thing I am going to warn you about though, is don't just set up the integral for the top half and then double it. Because that may not actually be accurate. That depends on the function, because the function may not be symmetric over that region. So we're going to definitely have to watch out for doing symmetry on regions, because that's only going to apply if the function itself is symmetric. But somebody was just chiming in.
Flip
asking
them.
something. You're good?
Yeah.
Okay. All right. Well, regardless, we need to get the equation of this circle so that we can solve it for y. All right. So what's the equation of this circle?
X squared plus y squared equals 4.
Good. So x squared plus y squared equals 4. So if we solve that for y, we get y equals plus or minus the square root of 4 minus x squared. And so when I was asking about where his head and feet are, Bradley said something about the feet were at the minus. And that's exactly the difference here. The plus square root is giving us the top, the positive part of this circle. The negative square root is giving us the bottom. So the bounds we're going to put on this are going to be on the bottom, negative square root of 4 minus x squared. And the top is going to be positive square root of 4 minus x squared. And this is going to happen sometime where the same curve is actually used to describe both head and feet. And we could easily set this up so that sideways, same thing would have happened, right? So sometimes when you get this, where it's the same curve, you're going to get different options as you solve for y or x. And you just got to pay attention to, you know, the positive versus the negative or whatever. Make sure you're on the right portion of the curve. Okay, so now that we've got that, now we can march along in the x direction. He's going to go from 0 out to 2. So here would be the bounds if we set it up as dy dx. All right, so now let's do dx dy where he's sideways. So we'll erase the vertical integration men. Let's put sideways integration men in here. So a few representatives. All right, so now if we look at head and feet, his feet are always at x equals 0. So that's nice. And then his head is always on the circle. But horizontally, it's the same part of the circle. If we were to solve this thing for x, we would see that we get the same thing, just reverse. So x is plus or minus the square root of 4y squared. So which one are we going to use for his head?
Two times root 4 minus y squared? No, never mind.
So we don't need to multiply by 2. We just need the positive one, because that's the positive x. So this one will be the square root of 4 minus y squared. Because the negative square root would have been the left side of the circle, but we don't have the left side of the circle right now. All right, and so then lastly, the y's, well, they're going to go from -2 up to +2. We can put those on. And so there is the other way of looking at this one. So again, without knowing exactly what f is, I can't tell you which one is better. But if it just comes down to the bounds, I'd much rather do the second one. Because think about it. I'm going to have to plug in one of these square root of things anyway. But if I go with the dx dy, I only have to plug in the one of them. The other one I get to plug in 0. That's awesome. Because then when it comes to just having y's left over, we have a less complicated thing to integrate, most likely. So this one, without knowing the function, I'm leaning towards the second. But I'd know for sure whether I want to use that second one or the first one, depending on what f is. Because again, the function itself that I'm integrating may not work so well horizontally. So how are we feeling in terms of this changing bound stuff? How about you give me a thumbs up if you're feeling okay with it?
Yeah, I feel pretty good about it.
Feel okay?
We're feeling all right? Okay. It comes with practice, and definitely you have to visualize the region. You got to draw the picture, right? Without seeing the picture, it's really, really hard to do this. So draw the picture. Get a feel for what the region is. That will definitely help you set it up either way, especially then going forward, figuring out which one's a better way to do it.
What if I can't draw the function?
But if you can't draw it or it can't be drawn?
I can't draw it.
Okay. Use your technology to help you, right? Grab a calculator, use Desmos if you've got access to the internet, something like that. Yeah, that's my recommendation right now, because again, without being able to draw it, it's awfully hard to figure out exactly what the bounds are. So this is just yet another one of those places where if I was that kind of math teacher, I'd be like, see, this is why we taught you how to do all that graphing stuff way back in pre-calc and algebra, and you really should have been paying attention so that now you can, right? Like, we can always do that in math where you can always reference back, but this is a case of, yeah, we're just adding on to things that we know. And graphing is actually super important in many places, and this is one of them, you know. So maybe one thing you can do is go back and kind of practice some of the general shapes, help you get a better feel for it. But yeah, without it actually being able to visualize this picture, you're going to be kind of in trouble when it comes time to actually doing it. I wish I could give you a better answer, Bradley, but we're kind of at that point where we need to know how to get the graphs. And the things that we're going to do, like the ones on your homework, are not going to be ones that have crazy graphs that you've never seen before or you can't figure out. You know what I mean? Like, we're not going to do that to you. But out there, right? Out there in the real world, if you're applying this to something, Lord knows what your region might look like, right? I mean, just imagine maybe we're doing some sort of here's an example where we might use a double integral. Maybe we're looking at some sort of population modeling of animals in the Tahoe Basin, right? And so what we need to do is actually map out the land region in some plot in Tahoe. And for those of you who are from Tahoe, you know that we don't do anything in rectangles, right? Show me a plot of land that's rectangular outside of maybe Sierra Tract, right? Or Al Tahoe areas, right? No, we have all kinds of weird shapes because of the streams and the meadows and the mountains and the lake and blah, 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 right? So you can just imagine how complicated your region might be if we're like, okay, well, we need to add up over this entire land plot. These things can get gnarly. So out there in the real world, they can get rough and nasty. On your homeworks, they should be fairly straightforward, things you've seen before that shouldn't be terribly difficult to find. So that's about the best I can give you with that right now.
Sounds good. Cockplot 3D it is.
Yeah, right. Okay. Well, notice that this is nothing about graphing the surface, though, right? Like, I don't know what f of x, y is. And myself, I don't usually concern myself with the picture of f of x, y. It doesn't matter so much if I'm told I'm looking over a given region. So, you just mentioned calc plot 3D, and that's the reason I'm bringing this up, is that the 3D-ness that comes from the f of xy is not as important as the region. Because without the region, without visualizing that, you can't set up the bounds, which means you have no chance of doing an integral, regardless of what that surface may look like. So, all right. Well, I'm going to do something to help you out, though, a little bit with a shape like this. Because this shape, yeah, it's all well and good, but in rectangular, this kind of blows. What coordinate system is just dying, is yelling at us, use me, use me, use me in this kind of picture?
Polar.
Yeah, polar. So I want to remind you about polar, and I want to show you how we can use polar to deal with these double integrals, because in lots of circumstances, going to polar makes life a lot easier. All right, so I'm going to keep this picture up because we're going to reference it again. I want to give you just a little bit of recap on polar because it's terribly useful. Okay, so remember the idea here is instead of an x and a y, we're putting an r and a theta. So r is a distance away from the origin, and theta is the direction that we're going. So if I have a generic point out here somewhere, r is the distance from the origin to that point, and then theta is what direction we want to head. So I just want to remind you that in everyday life, we use polar a lot for directions, right? If someone's like, oh yeah, where's the grocery store? Well, you go that way about 2 miles. I just told you a direction and a distance, 2 miles down the road, right? So we do that a lot, where we say it's over that way about 7 meters, right? So if we have a distance and a direction, that's plenty to actually show where something is. And that's what polar coordinates does. And then polar coordinates, there's a way to convert between that and your XY. So let me just remind you of those real quick. The conversions are x equals r cosine theta, and y equals r sine theta. And that just comes from the right triangle. Right? If I were to actually put those x's and y's on here, they're the horizontal and vertical distances. And so this literally is just coming from that right triangle. So given r and theta, this is how you get x and y. You can go the other direction. We know that theta, the tangent of theta, is actually y over x, and we get the r from the Pythagorean theorem, x squared plus y squared. So those are your two sets of conversions if you ever want to bounce back and forth. For the context of double integrals, it's the x equals r cosine and the y equals r sine. Those are the ones that you're going to want to know. Because almost always when we're doing this, we're going to be converting from rectangular to polar to make the integral easier, because it will make the bounds a lot easier and so on. Okay, so these are polar coordinates, right? Now, when it comes to what we're doing, we're going to use polar coordinates, or we're going to use polar coordinates when our regions are portions of circles, if they've got symmetry about the origin. So other things would be like an ellipse would be a good thing to use it on. Any of those weird polar shapes that we saw, cardioids, roses, lemniscates, limicons, like all those weird, and if you're just going, holy shit, I don't know any of these words and what you're talking about, These are all just different shapes you get when you graph in polar. I'm going to have you reference, I'll find a section in this book to let you know what you should go look at if you're not familiar with it. But if you're not familiar with the names of the shapes, don't worry about that. But whenever we get those kind of weird curvy things, yeah, Seamus just said they are annoying and cool simultaneously. I agree with the second part of that. I don't know that they're annoying. They're unfamiliar. How about we say that? They're unfamiliar, but cool, right? But yeah, so anytime you're in one of those kind of situations, one of those shapes, we definitely want to use polar. All right, so the question is, how do we adjust this so that we're in polar? Well, first, let me show you why this would be nice if we were going to do this in polar. So think about this as a polar region. So we'll have our f of xy. Now, there is going to be something that we have to put in here for our dA, and we'll worry about that right in a minute, but this is our dA. But suppose that this dA, we're going to say like it's a dr d theta, let's say, right? Or it's going to have a d theta dr. It's basically how it's going to work out. But I want you to think about this in terms of getting this region with angles and radii. So now think about this semicircle, this little region in here. The R's are all between 0 and 2. So no matter where you are in here, choose your favorite point, right? Like this one, or that one, or this one, right? No matter what, the R value is always going to be between 0 and 2. And then similarly, the angles, the smallest that angle is going to be is minus pi over 2, because that's straight down. We work our way to 0, and then we work our way up to pi over 2. Notice that if we're going to try to do this region in polar, our bounds are all constants. So this is the equivalent of a rectangle. This is the polar equivalent of a rectangle. I agree, Victor. Very cool. Because now when it comes time to integrate, oh, I love just having numbers to plug in. Right? Oh, look at that. Less annoying. Awesome. I will take that as a win. Well, you say that now, just because I'm talking about the bounds. Because there's some other stuff we're going to have to take care of when we do this. But you can start seeing the rationale behind this. Why maybe using polar is a better idea in certain circumstances. All right. Now, if we're going to do this, we have two things that we have to deal with. All right. The first is our function, right? You notice that this is f of xy. If we're going to convert the polar, I can't have any x's and y's. I can only have r's and thetas. So what we're going to have to do here is we're going to have to plug in the r cosine and the r sine for the x and y respectively. So we're going to have to change our function. So think about just like a simple function, like if it was xy. Well, now it's going to be r cosine theta times r sine theta. Right? Or think about that horrible one that we had to do earlier. That was the like xy sine of x squared y. That would be a horrible one to convert to polar. But luckily that region was rectangular, so we wouldn't want to do that. But every x, you're going to have to replace r cosine theta. Every y, you're going to have to replace it with r sine theta. Okay, so that's the first thing we're going to have to do. The second thing we're going to have to do is we're going to have to replace this dA. Instead of dx dy, we need to have dr and d theta. But here's the problem. This guy dA, it is not equal to dr d theta. In rectangular, it was fine, right? In rectangular, dA was definitely just dx dy or reverse. But in polar, it's not a direct translation. We can't just go to dr d theta. Ugh. Well, Seamus, this is where it's going to get a little more annoying.
Oh boy.
It is what it is, right? But let me kind of show you what's going on. So remember before, the reason it was dx dy was because we were looking at the area of a little chunk if we took a step in each direction, right? So we had a little differential in the x, a little differential in the y, and what that ended up giving us was a rectangle. And its area, dA, was width times height. Okay, so that's where that came from. But now that we're in polar, I want you to think about what happens if we take a little step in r and a little step in theta. So here's our point. I'm going to take a step in r. So there's a radial line coming through here, right? So my step in r is going to take me out, say, here. Okay, there's going to be my dr. But then I also need a d theta. Well, d theta, I'm going to exaggerate this a bit so we can see it a little bit better. But there's my d theta. So think about what this does to this region. This point right here gets swept along that angle. And so too does this one that's out further. So notice now, this is our dA. But it's not a rectangle. Uh-oh. Okay, so it's not a rectangle. That's why we can't just do dr times d theta. It doesn't work that way when we're in polar. However, we can figure out what it is. So that's what we're going to do here real quick. All right, so let's see if we can figure out what that little dA actually equals. All right, so I got a question. I don't know if anybody remembers. Do you remember how to find the area of a sector of a circle? Like the area of a slice of pie?
It's, you multiply by the cosine of the angle, right? Or
Okay, so cosine of the angle with the question mark, and Victor said something about sine of the angle. Turns out you don't use any sine or cosine.
oh, it's the angle divided by 360 multiplied by the area of the circle, right?
Okay. Except we're not going to use 360.
Oh, it's sorry, 2 pi.
Yeah. Again, you're lucky I can't throw this through the screen. So so yeah, we're gonna use radians, but yeah, that's exactly the right idea, Jacob, because like basically what you would do. Let's go back to the circle, and we're gonna look at the area of this little region. You set it up as a ratio. You go, okay, that area to the area of the circle is the same ratio as its angle is to the angle for the circle. So there's the divide by 2 pi, right? So you get your area is equal to theta times pi r squared divided by 2 pi. So the pi's cancel. So you get 1/2 r squared theta. So that's the area of a sector of a circle. And so what we're going to do to find this dA is take the bigger one and subtract the smaller one, right? If we take this bigger sector and we subtract the smaller one, that'll get our dA. So let's do that here. So dA is going to equal, so the bigger one is going to be 1/2 times its radius, which if we call this guy, say, R, it's R plus dr squared. And then the angle, of course, is d theta. And then we're going to subtract from that the smaller one, which is going to be 1/2 r squared d theta. So before we manipulate this and simplify it, are you cool with how I found it? Big pizza slice minus smaller pizza slice. So this is like the remnant. This is the crust, right? It's the crust of your slice of pizza after you've eaten all the good stuff. Although my son would argue he likes the crust the most. He's a freak. I don't know. Sometimes I wonder if there's hope for him as a mathematician and physicist if he thinks like that. You would expect my son, who is like a poli-sci communications major, to be all messed in the head, but you know, come on. Okay, that is true. Some crusts are actually really good. But pepperoni, cheese, like that is clearly where the money's at on your pizza. Just saying. All right. So let's go ahead and see what this ends up giving us. Well, if you distribute it out, I'm going to pull out the 1/2 and the d theta because we already know that that's all there, right? The rest of it, let's simplify. So we're going to get an r squared plus 2r dr plus dr squared minus r squared. So those r squareds cancel. All right, now we're going to do one thing that you may not like, but I'm in charge, so I get to do what I want. No, here's what we're going to do. This piece right here, think about dr squared. Dr is a little tiny step in the r direction, right? So it's already like infinitesimally small, super, super small. Well, what happens when you take something super small and you square it? Well, it's also super small, right? But as Victor says, it's a lot smaller. So this one, dr squared, is very small. I mean, like crazy small, especially compared to this other piece. It's so small that you won't even notice it compared to the other one, right? It'd be like Bill Gates. He finds a $100 bill on the ground. He's probably like, yeah, whatever, $100, I don't care, right? Because it's so small compared to his net worth. It's kind of the same thing here. This dr squared, it's like pennies compared to these millions. So that's so very small, we're going to ignore it. So basically, it's so close to 0, it is B0. All right, so if we kind of let that one disappear, then what we've got is 1/2 d theta times 2r dr. So the 2's cancel, and we're left with r. I'm just going to rewrite it. So we get r times dr times d theta. So the little differential chunk of area now is not just dr d theta, but we also need to multiply it by an r. But if you think about it, it makes sense. Think about that chunk of crust that's left over. Let's fix theta. Okay, so let's just keep theta how it is. And let's keep dr what it is. So it's the same thickness of this crust. But if I were to come in really, really close, there's not going to be much crust left. If this slice is really huge, right? Like go get one of those gigantic, incredibly large pizzas that are, now that same crust is going to be much bigger areas. It's further out. So it should make sense to you that this area chunk depends on where we are. How far away are we? Not just how thick is the crust or what kind of angle we went with. Think about it this way. Remember arc length? S is equal to R times theta. Well, that arc length, if you want to think about it, sort of the edge of the rectangle here, that arc length increases with R. So I know it's a little bit weird, but it's necessary that when we do this dA chunk, we actually throw in the extra R. All right, so there are two things we have to do then. We have to convert our function into R's and thetas, and then we have to throw in this R times dr d theta for our dA. So we don't have time to actually do any right now because we're almost out of time for today. But I do want to give you one way to help remember what we put in. And this is definitely silly. This is a Bruce thing for sure. For those of you who know me, you're going to go, yeah, this is not right. For those who don't know me, you're starting to figure it out. But here's what I always say. When you convert the polar, don't forget that you have to stop like a pirate. Right? Because what we need to add in is a RD theta. I told it becomes a pirate thing, right? So it's RD theta, pirate, RD theta. So you'll hear me say that all the time. I will use the stupid pirate voice, but you'll never forget it. You'll always remember that we need to put in the R. And what we're going to see as we continue in this discussion of multi-variable and multiple integrals is that we do this kind of trick all the time where we change our viewpoint into another coordinate system. And every time you do that, you introduce the possibility of having to put in something here. It's called a Jacobian, is the name for an element that we end up multiplying in when we do a transformation to a different coordinate system. And so we're going to see Jacobians pop up again. In fact, there's a whole section where we'll calculate Jacobians given specific transformations. But in the case of polar, that Jacobian is R. So we always have to change that area to RD theta. All right, so what we'll do on Wednesday is we'll do some examples of this. We'll take functions that we're integrating over regions where polar is the way we want to go. And you'll see how doing this conversion can make things a lot easier depending on the region and the function. All right, so with that, anything else that you guys, any questions on the record before I pause it? Oh, actually, yeah, one more thing. We have our first exam on Friday. Might as well mention this now.
Yeah, I wanted to
And,
ask you
it's
questions
gonna-
on the exam.
So in terms of what it's going to cover, it's going to go through 5.2. All right, so it will include double integrals, but just double integrals over general regions, none that we're going to use polar to convert to, but you definitely should know how to swap bounds and do that kind of stuff, okay? So it will be chapter, I think it was chapter 3 that we were in where we were doing all of the vector value function stuff. So vector value functions, and then the first 2 sections of chapter 5. In terms of more about the exam, we'll spend some time on Wednesday reviewing it after we talk some more polar coordinates. So we'll talk more details then, but if you want to just start getting a heads up on it, those are the sections it's going to cover. It's very similar to quizzes, just more, right? Because quizzes usually were just like a section or 2. This exam is going to be on like 6 sections or something like that. So just expect similar to quizzes, just more.
What did you say they were from? The beginning to what?
5.2.
5.2.
5.2.
5.2.
And Bruce, so do you
it's chapter
recommend?
3.
Sorry.
No, go ahead.
Do you recommend studying for your exams similar to how we've studied for the quizzes? If we've been doing well on the quizzes?
Absolutely. Yep, absolutely. Because it's going to be very similar. I'll make you think a little bit more on the exams, right? The quizzes, as you've noticed, have been really just like procedural. Do you know how to do the things? So there definitely will be that on the exam, but there will also be more, are you understanding the concepts? So you definitely should look at that as well. But I think studying kind of like you've been studying on quizzes is definitely good for all the procedural stuff.
How should we study for the non-procedural stuff?
Know the material. I mean, I don't know how to answer that other than
Gotcha.
like it, because math is not just a process, right? Like, yes, there are things that you should know how to do. You should know how to do the steps to calculate curvature. You should know how to do the steps to find a double integral. But you should also know, what is curvature doing? What is it actually telling you? How does it relate to other stuff? Right? And I think that's kind of what I'm getting at as the things that are not procedural. Another thing I'm going to recommend, since I've never taken one of my tests, ask people in the class who have had me as an instructor before, and ask them these questions, because they'll have a better understanding. The one thing I'm going to warn you and them about is that they already saw that like the physics exams are a little bit different than math exams. Remember that this is a math class, not a physics class. And for a lot of you, physics and Bruce has kind of been synonymous for a while. So, but that's my recommendation there, Seamus, is you've got a bunch of people in here who know what my tests are like, and they probably will give you a better answer to it than, well, I don't know the stuff, which is my answer.
All right, thank you.
Yeah, you're welcome. And I realize that kind of comes off as sort of a dickish statement, but and it's kind of how I feel. Like whenever anybody asks, well, what's the important stuff to study? I'm like, everything we talked about. If it wasn't important, I wouldn't talk about it, right? So anyway.
How many questions typically are your tests, Bruce?
406.
Gotcha.
No, I have no idea. My recommendation there is don't worry about that, right? Because what if I told you there were 5 questions? Is that going to change how you study than if I tell you there's 8?
Probably.
Or 12? Really? It would change how you study?
Yeah, because then I would know you're going to ask, I'd focus on the 5 main things instead of,
well, what are the 5 main things?
I don't know. You'll have to give me an hour to decide that.
Right? And then, but what if one of those questions has multiple parts? Right? So, like, I get it. I know that that's a real common question too. I won't actually know the answer to that until I write it. And, it's kind of irrelevant, honestly, because I'm going to ask you about all the important stuff. And whether that means it's 5 questions or 10 questions or 8 questions, 3 that have multiple parts or whatever, I'm going to get at the important things. And if you have studied, if you've been paying attention, you'll know those important things and you'll do just fine. It might hurt a little bit during the exam. I think I have a reputation of giving really, really hard exams. Victor just said, be prepared to cry. So I know I have this reputation, but I know I'm also really fair when it comes to grading them. But yeah, I want to see what you know, and I want to see how well you know it. And if you don't know everything, that's okay, right? Very few people, the first time they go through anything, know everything. But, it's just a test, which is also something that most people can say, oh, that's real easy for you as a teacher to mention. But it is. It's just one exam. If you end up doing poorly on it, no big deal. As long as you've been doing all your homeworks, I drop it. And, you know, again, it's only one test in one class in your entire college career, which is just a blink in the eye of your life. It's not really that big of a deal. Easier said than done, right? Anyway. But we'll talk more about the exam. Maybe help make you feel a little bit better about it on Wednesday. But at least you know where to start. All right. All righty. Well, I guess with that, we'll go ahead and sign off for the day. And I will see you all on Wednesday.